Data modeling is the foundation of any successful business intelligence endeavor. It involves organizing and structuring data in a way that makes it easy to understand, analyze, and extract meaningful insights. A well-designed data model ensures data consistency, improves query performance, and empowers users to make informed decisions. Think of it as building a blueprint for your data, ensuring that every piece of information has a designated place and relationship to other data points. In the realm of Power BI, a robust data model is crucial for transforming raw data into interactive dashboards and reports. It enables you to connect to various data sources, combine data from multiple tables, and create compelling visualizations that tell a story. Without proper data modeling, your Power BI reports might be slow, difficult to interpret, and ultimately fail to provide the insights needed for effective decision-making. A well-structured data model in Power BI typically consists of fact tables and dimension tables connected through relationships. Fact tables store measurable data points, while dimension tables provide context to those measurements. For instance, in a sales analysis model, a fact table might contain data on sales transactions, while dimension tables could include information about products, customers, and dates. By carefully designing your data model, you create a solid framework for analyzing your data. It's akin to organizing a library where books are categorized and shelved systematically, making it effortless to find the information you need. A well-modeled dataset in Power BI empowers users to navigate through data seamlessly, answer complex business questions, and uncover hidden patterns that would otherwise remain obscured. In data modeling, fact tables and dimension tables are fundamental. Understanding their roles is crucial for a robust data model. Think of it like building a house. Fact tables are the bricks representing core data, while dimension tables are the doors and windows providing context. Fact tables store numerical data that can be aggregated. They represent the what of your analysis: sales, visits, production units. Each row in a fact table corresponds to a specific event with columns containing measurements. Dimension tables provide descriptive attributes that add context to the facts. They answer who, what, where, when, and how about the data. A customer dimension table stores information like customer ID, name, and demographics. The relationship between fact and dimension tables forms a star schema. This structure allows you to analyze data from multiple perspectives. By defining fact and dimension tables, you create an efficient data model. It enables Power BI to process queries efficiently and provide insights for informed decisions. Before diving into the intricacies of data modeling, it's crucial to ensure your data is clean, consistent, and ready for analysis. Raw data from various sources often comes with inconsistencies, errors, and formatting issues that can hinder accurate reporting. Data cleaning and transformation, therefore, are essential preparatory steps in the data modeling process. Think of it as preparing ingredients before cooking a meal. Just as you wouldn't use rotten vegetables or stale spices, you wouldn't want to build a data model on inaccurate or inconsistent data. Power BI's Power Query Editor provides a powerful and intuitive interface for cleaning, transforming, and shaping your data before it's loaded into the model. One common data cleaning task is handling missing values. Power Query offers various techniques for dealing with nulls, such as replacing them with a default value using the previous or next value, or completely removing rows with missing data. Another crucial aspect is ensuring data consistency. For instance, if you have data coming from different sources with varying date formats, Power Query allows you to standardize them into a single consistent format. Data transformation involves restructuring your data to make it more suitable for analysis. This might include pivoting or unpivoting columns, splitting or combining columns, grouping data into categories, or applying mathematical calculations to create new fields. Power Query's graphical interface makes it easy to perform these transformations without writing a single line of code. By investing time in data cleaning and transformation, you lay a solid foundation for a robust and reliable data model. Clean and consistent data ensures accurate calculations, meaningful insights, and ultimately better business decisions. Remember, garbage in, garbage out. The quality of your data directly impacts the quality of your analysis. Section 4. Establishing relationships and creating measures with DAX. Once your fact and dimension tables are defined and data cleaned, the next step is establishing relationships between tables. These relationships enable seamless and accurate data analysis from multiple tables. In Power BI, relationships are created by connecting a primary key in one table to a foreign key in another. For example, link the customer ID in the sales fact table to the customer ID in the customer's dimension table. This allows Power BI to understand how data points in different tables are related. With relationships established, use DAX to create calculated columns and measures for new insights. DAX is a specialized language for advanced calculations and data manipulations. Calculated columns add new data points based on existing columns within the same table. For instance, calculate total profit by subtracting cost price from selling price in the sales table. Measures perform calculations across tables, leveraging established relationships. For example, create a measure to calculate total sales for a product category by summing sales amounts. Establishing relationships and creating DAX measures unlocks the true potential of your data model. It empowers you to ask complex questions, explore data from multiple perspectives, and gain deeper insights. Section 5: Star Schema versus Snowflake Schema. Choosing the right data model. When designing a dimensional data model in Power BI, you'll often encounter two primary schema designs: Star Schema and Snowflake Schema. Both approaches aim to organize data for efficient analysis, but they differ in their complexity and performance characteristics. Choosing the right schema for your specific needs depends on factors like data size, complexity, and reporting requirements. The star schema, as previously mentioned, resembles a star with a central fact table connected to multiple dimension tables. Its simplicity is its strength, making it easy to understand and query. The direct one-to-one relationships between the fact table and dimension tables lead to faster query performance, as data retrieval involves fewer joins. However, this simplicity can lead to some data redundancy. For instance, if your dimension tables contain hierarchical data, like product categories and subcategories, you might have the same category information repeated for multiple products. The Snowflake schema, on the other hand, takes the star schema a step further by normalizing dimension tables. It breaks down dimension tables into multiple related tables, eliminating data redundancy and improving data integrity. Imagine a product's dimension table being split into products, categories, and subcategories tables. While this normalization reduces data duplication, it comes at the cost of increased complexity. The multiple joins required to retrieve data in a Snowflake schema can potentially impact query performance, especially for large data sets. Choosing between a star schema and a Snowflake schema involves a trade-off between simplicity and normalization. For smaller data sets with straightforward reporting requirements, the star schema's simplicity and performance advantages often make it the preferred choice. However, if you're dealing with large, complex data sets with a high degree of data redundancy, the Snowflake schema's normalization benefits might outweigh its performance considerations.